Welcome to the Explainer. Today, we're going to crack the code on a type of math problem that looks, well, pretty complex on the surface. But as you're about to see, it's hiding a surprisingly elegant and actually visual solution. We're talking about polynomial inequalities.
Okay, let's just dive right in. Take a look at this problem on the screen. Now, if you're faced with this, what's your first instinct? You'd probably start plugging in random numbers, right? You test 0, then maybe 1, then a negative number, and it just gets really messy. Plus, you can't ever be totally sure you've found all the right spots.
Yeah, that's the tedious way. But what if I told you there's a powerful technique that just completely transforms this algebraic headache into a simple, easy-to-read picture, a method that's going to give you the right answer every single time?
So this smarter way, it's a technique called the generalized method of intervals. You might also hear it called the Wavy Curve Method, and trust me, you'll see exactly why in just a minute. It is one of the most useful tools you can have for problems just like this.
I want you to think of this method kind of like a GPS for the number line. It literally creates a simple visual map that tells you exactly which regions, which intervals, are the right ones for your inequality. It completely gets rid of all the guesswork. No more randomly testing points.
And look, this isn't some kind of math magic. It's an algorithm. It's just a simple, repeatable process that works every time. So let's break down the 4 key steps we need to create this visual map.
It really just boils down to these 4 things. First, you find your critical points. Think of them as your boundaries. Second, you plot those points on a number line. Third, you figure out the sign, plus or minus, on the far right. And fourth, you just alternate the signs as you move left across each point. That's the whole game right there. Now, let's talk about this idea of a critical point. What is it? It's any value of x that makes one of those little parentheses chunks equal to 0. And why are they so important? Well, because these are the only places where the whole expression can flip its sign from positive to negative or back again. They're basically the hinges for the entire problem. Okay, theory is great, but let's see this thing in action. We're going to take that 4-step method and apply it to that intimidating problem we started with, and you're going to watch it become super simple.
First things first, a little housekeeping. This method works best when all the x terms are positive. You see that 1 minus 2x term? We want to flip that. So we'll multiply the whole inequality by -1, which turns it into 2x minus 1. But, and this is absolutely crucial, anytime you multiply or divide an inequality by a negative number, you have to flip the sign. So greater than 0 becomes less than 0.
All right, on to step 1. Find those critical points. We just set each piece to 0 and solve. Super easy. That gives us our 3 boundary points, x equals 1, x equals 2, and x equals 1/2.
Step 2, piece of cake. We just take those 3 points, 1/2, 1, and 2, and we pop them onto our number line in the right order. And you can see, just like that, they've split the entire number line into 4 distinct regions or intervals.
And now for step 3. This is the cool shortcut. Because we did that little bit of housekeeping and made sure all our x terms are positive, we get to use a simple rule. The interval on the far right to the right of our biggest number, 2, is always going to be positive. So we just put a plus sign there to get started.
And here it is, the wavy curve in all its glory. Starting from that plus sign on the right, we just draw a curve that crosses the number line at each of our critical points. And every single time it crosses a point, we just flip the sign. So we go from positive, cross over 2 and become negative, cross 1 to go back to positive, and finally cross 1/2 to become negative again. Okay, we have this cool-looking map. Now what? Well, we have to go back to our actual question. Remember, after we simplified it, we're looking for where the expression is less than 0. So on our wavy curve map, we're looking for all the intervals where we put a minus sign, all the regions where our curve dipped below the line.
Our map just hands us the answer. It clearly shows 2 negative regions, everything to the left of 1/2, and that little slice between 1 and 2. So our final answer is just the combination of those 2 intervals. And that's it. A complex problem solved with a simple picture.
But the real beauty of this technique isn't just that it works for that one problem. Its true power is just how versatile it is. It can handle way more complex stuff.
For instance, I know what you might be thinking. Okay, sure, that works for neat little polynomials, but what about rational inequalities? What about messy fractions with stuff on the top and bottom? Surely that complicates things, right?
Believe it or not, it doesn't at all. The method of intervals handles this stuff perfectly. You just find the critical points for the numerator and the denominator separately, plot them all on the same line, and then use the exact same wavy curve logic.
The core process stays identical.
Okay, but what about something really tricky, like an inequality with absolute values? You know, these are the ones that are usually a total nightmare to solve, because you have to break them into a million different cases.
You bet. Even this falls to our method. With just a clever little substitution, recognizing that x squared is the same thing as the absolute value of x squared, we can factor this and use the exact same interval logic to find the solution. It's an incredibly robust tool.
You know, there's this great quote by Eskitter that just nails what we've been exploring today. The method of intervals is a perfect example of mathematical elegance. It's all about taking a problem that feels messy and complicated and making it visually simple. And that's really the big idea to take away from this. Sometimes the most challenging problems don't need more brute force. They just need a better method, a different perspective that turns the whole problem on its head. It makes you wonder, right? How many other hard problems out there are just waiting for the right way to be seen?